Okay.
Yeah.
Okay. Thank you. Excuse me for the delay. Thank you for your talk, Victor. It's very interesting and important problem for database with chemical compound. I will say about same problem, but I will say as it will as a talk, because I present not soft but some solve task. For example, dear ladies and gentlemen, I present your attention report on the topic structural building units of homoleptic coordination compound. I am from Mara State University, Technical State University. The context, please say next slide, please. The contents of my report are present on this slide. Here is a quote from Jan Lee Kuhn. Then artifact intelligence is good assistance for solving scientific problems, one of which we will consider as an example. Please, next slide. First of all, my talk will focus on the data that can be extracted from crystal structure, as well as use for machine learning. It is now the success for solving a given problem significant depend of the set of data and their quality. Chemists have worked off a lot of with data for a long time. So one of the first expert systems diagnosed the result of mass spectra back in 1960. This fact is not surprising since many chemical compounds are known. One must be able to find among the enter on the one need or with the recurrent properties. Please, next slide. Chemists are still active using modern data analysis method. The wide variety of chemical and the wide variety of chemicals is the main incentive for this. For example, the WCAG Cambridge Structure Database now contains 1.25 million entries at its zinc database, which is used to discover new drugs, contain 10 of millions of compounds. This data is extracted from Cambridge database. Only machine methods are suitable for processing such large amount of information. Chemical problems can be solved with the help presented on the slide. It's previous slide. We use machine learning to determine the oxidation state of metal atoms in the structure of coordination compound. For what purpose is it necessary to determine the oxidation state of metal atoms? An important descriptor of metal atoms, which determine the ratio of structure building units in the crystals. Many properties of crystal structure depend on the oxidation state of the complex atoms. Information about oxidation state of the metals is necessary for intelligent assemble crystal from structure building units. How to oxidation state? No, please, previous slide, please. How the oxidation state of metal atoms determined? According to physical properties of crystal, color, redox activity, magnetic properties. According to balance charge of ligands, outer sphere particles, and metal atoms, then is oxidation state. Based on result of quantum chemical calculation and coordination compound. I talk about when I use SBU. SBU is used in my report, not secondary building units. Since a chemical synthesis complex, usually from ligand and metal cations, Secondary building units can be identified in the crystal structure with cluster topological simplification. They are aggregate or several ligands and metal atoms. At the first glance, the task is simple, how we see in thin complex shown on the left. But many other ligands are known, some which acutely complex, as a figure on the right. In such case, it is not easy to determine the charge of the ligands, for this is equal to 6. We can found no, please, previous slide, excuse me. We can found in our service ligand for this code. I will talk after about it. It is necessary to know charge structure building units in order to determine oxidation state of metal atoms by the Serre balance of the crystal structure. How is this? It's plus, 2 plus, and 4 plus sulfate anion. Please, next slide. No, the complex structure in ligand is not only a problem for this approach. This structure, crystal structure, may be incompletely determined. How this ligand can be radical on radical ions. An example in shown figure on the right. A large amount of data future complicates the task of determining the charge of ligands. So the following methods are used. Calculate the hardness of and energy of SBU formation using the fast quantum method MOPAC. For SBU with an optimal charge, the radius parameter should be maximum and the formation energy should be minimum. Determine charge of comparison with the neutral form SBU, which is obtained by automatically adding the missing hydrogen atom to it. Summation of positive and negative charge in the SBU smiles. The method proposed in articles Rivers and its co-authors. Jablenka and his authors use machine learning to determine the oxidation state in these articles. Please, next slide. Our data same, which we present on the slide, is similar. It's similar to the used in Jablenka work. It contains first stage: selection crystal structure data, creation sample description data table, data markup, statistical analysis, clean as transformation of data, and development of decision model. Please, next slide. We use the Topos Pro and Python and Excel software packet for preparation and processing data. Also, we take data from our topological collection. Here is present. Data we extracted with user topological service. Please, next slide. To calculate SBU descriptor, Topos Pro used various algorithms. One of them is assessing the shape of the coordination figure using angular fingerprints. Its description is present on the slides. Its description is presented on the slides. We use the descriptor for characterize shape of coordination figure of metal atoms. Please, next slide. Of course, I would like to take all the GNOV structure data and use it for training. But this first, in our case, there are a lot of such data, and contain errors, inaccuracies, and contradiction. Therefore, we decide to limit ourselves to their structure homoleptic coordination compound, which the chemical type of ligand is uniquely correlated with the entire crystal structure. We select from Cambridge structure database and inorganic structure database according to following condition. They are coordination compound consisting of metal atoms, ligands, and outer sphere particles, which are referenceable of as structure building units of a crystal. The structure contains only one type of ligands. There are no restriction on the number and nature of metal atoms and out-sphere particles. The positive metal atoms are order. They are completely occupied by metal atoms of the same chemical type. We select from CSD and ICSD 39 structure studies, and let's follow numbers of other data. It is big data, and this big data we use it for solving our task. Please, next slide. By analogy with object-oriented approach, which is actively used in programming, our structure of RCC, homoleptic crystal structure, be considered a single object that has certain properties or rare set of properties values with probability of the implementation, such as crystal color, for example. More probability is colorless. Melting temperature for this compound, periodic crystal structure. The distribution built for only CSD, because only CSD contains this information. We see different samples ICSD and CSD with same compound. CSD contain only more molecular complexes, and ICSD contain framework complexes. Please, next slide, please. Metal atoms are characterized by set of other properties. This is nature of metal atoms. In CSD and ICSD, we see difference between distribution. In CSD contain atoms from transition element from for the period, but ICSD contain alkaline earth metal. Here also present distribution by oxidation state of compound. We see the distribution very unbalanced. Some, please, next slide. Also, metal atoms characterize composition of coordination polyhedra and coordination figure. The distribution present in the tables. We see difference between CSD and ICSD. CSD contain big molecule usually, and some coordination polyhedra is mixed between two atoms. Else, ICSD contain more only one atom environment. Please, next slide. For solve our task determination oxidation state, we select we need in number for build space of feature. We take for character for feature the next descriptors. It is 27 dimension space. If we take some compound, we get fewer descriptors, because some descriptors equal 0. as example for complexes silver 2 in this. Please, next slide. We choose random forest for accelerating algorithm. We identify the most important descriptors is here from the complete list of features and optimize hyperparameters of our model. The prediction results are shown in table on the right. They are pretty good both for cross-validation, it's here, and test sets. Despite the strong imbalance of the distribution of metal atoms by oxidation states. Please, next slide. This is clearly visible in the presented graphs, where most of points are located on the red diagonals. Metals for which the prediction result don't correspond to makings are also shown here. It's here. At the bottom of the slide, are example of specific structure from CSD and ICSD, which such discrepancies with a high probability of the predicted value. It's a value more probability and chemical corrected. Maybe it is error, but it's need more complex check it. Please, next slide. The reason of the maybe difference, they are not only prediction error, nevertheless there are also error in their entering into the database on the 4-lead cyanamide. It is plumbum, lead 4 plus. Lead 4 plus was in database. Error by the author of the such work, as well as making of oxidation state that we did. We are now making correction of the errors in the last paragraph. With all this, our model has good predictive power. Jungling by the quality criteria. For example, it correctly determines oxidation state of all cesium atoms in the cesium 7 oxygen electride with a full agreement with the result of quantum chemical calculation of its structure. Not monovalent but divalent copper is predicted with high probability in the structure presented on the slide in the left. The compounds have green color, crystal compounds, crystal have green color. Please, next slide. It is incorrectly confirmed by both title of these articles and the green color of the crystals. Green and blue colors are characterized divalent copper complex. It is determined only by the copper 2 cation. Blue, green, it is probability see the color in crystals. Monovalent copper complex, according to decision 3 present on the slide that was built for the HCC structure, will be colorless with probability 0.38%. Please, next slide. At the end of my report, I would like to introduce the web service that we developed at the Samara Center of Theoretical Material Science. Firstly, there is a service for predicted oxidation state of metal atoms built for this model. Now it's work for any metals and any environment. Secondary, this is a service of analyze the environment of metal atoms in the HCC structure. The user selects the chemical varieties in central atoms and its surrounding atoms. Optionally for environment and geometrical characteristics of central atoms are displayed on the screen. Please, next slide. We also developed a dashboard which currently is in the testing stage, but has already helped us find some patterns in the HCC structure. The dashboard allows you to see various distribution for the geometrical characteristic of metal atoms in dynamic. The dashboard built in the Excel, but we plan it relies in web service. Екатерина Barabana will talk more about it at the 7 SPD collaboration meeting and workshop on information topology in natural science in Samara. His report is scheduled for Friday of this week. Please, next slide. This, as a result of our research, universal schema has been created that make it possible to predict the oxidation state of metal atoms based on the characteristic of their Voronoi polyhedra interstructure of various coordination and ionic compounds, as well as organometallic coordination polymer among them. We have created an MMC dashboard and web service that provide access to information about the HCC in the HCC, SBUs in the HCC structures. Next, we plan to use the HCC samples to predict the crystal structure of coordination compound, namely the chemical composition, unit cell parameter, and structure and space group of symmetry, as talked in Nadezhda Nikolaevna in first reports. But we do for organic compounds. And please, next slide. Certainly, a predictive model for large data set is a labor-intensive endeavor. It would have been impossible without the help of my colleagues, import device and recommendation of my supervisor, Lisaf Tojiblatov, alternatical support for the Russian Science Foundation. Please, next slide. Let's slide. I thank dear listener for your attention and hope that my report will be useful for you in some way. Thank you for attention.
Yeah, thank you very much for your nice talk. And since we are almost out of schedule, but nevertheless, I believe that we've got a time for a couple of questions. So please.
Виктор Анатольевич, один вопрос мне. Ну, what other machine learning methods can be used for solve your problem? We use it only random forest algorithm.
Yes, yes.
Maybe it's better to use another more efficient algorithm of machine learning for solving your problem. Alexander Fedорович, что-то другие алгоритмы.
Yeah, I understand. We try different algorithms. It's not only random forest, but supervector meshing, logistic regression, and natural network. Natural network get more efficient, more good result, but its model is more complex and long work. We compare to algorithm between in
accuracy.
Yes, for result. We use random foreigns in provision investigation for coordination compound in oxygen environment. And in the articles, investigate other algorithm.
Thanks.